3.4, polynomial functions, graphs, applications, and models. Example 1a starts with a graph. And to be honest, you should probably already know what this looks like. An x to the third function looks kind of like this. Here, let's fix that. But it's shifted up 1. So we already kind of know what it looks like. I think one way to do it is to make an XY table. And we can plug in numbers like this. And if you plug in -2 cubed, -2 cubed is -8, plus the 1 gives me -7. -1 cubed plus the 1 gives me 0. 0 cubed plus 1 is 1. 1 cubed plus 1 is 2. And 2 cubed is 8, plus 1 is 9. So we can graph points like that, okay? Let me zoom in a little bit. We've got -2, -7. -1, 0. 0, 1. 1, 2. And 2, 9. There. So I kind of visualize this as like almost like a parabola with one of its arms twisted. Okay, imagine a parabola, but then twist one of the arms down. That's kind of what this thing looks like. But that's an x cubed that's been shifted up 1. The next question says something about determine the largest open intervals of the domain for which each function is increasing or decreasing. Increasing. This thing's increasing the whole way. It's going uphill. If you read it from left to right, and that's what you're supposed to do, read it from left to right, this thing is increasing the whole time. So if it's increasing the whole time, that's going to be all real numbers. It's increasing for the whole domain. So we've got a couple of graphs here, and I know you don't know it yet, but a graph like this, when it says x to the 5th, odd powers of x behave an awful lot like x to the 3rd. So it's going to look something like x to the 3rd. It's not going to be exactly x to the 3rd, but it's going to look something like that. Looking at the shifting, you should be able to see that whatever this x to the 5th does, it's going right to. Okay? So it's going to look something like that, but it's going to be shifted over to the right too. So when I make my table, instead of putting 0 in the middle, I might put right 2 in the middle. You can plug in whatever you want, but it makes sense since we're shifted right 2 to put 2 in the middle. So if I plug in 0, you're going to have -2 to the 5th, which is -32. And plug in 1, you'll have 1 minus 2 is -1 to the 5th, is -1. Plug in 2, 2 minus 2 is 0. You have 0 to the 5th, which is 0. Plug in 3, 3 minus 2 is 1. You're going to have 1 to the 5th, which is 1. And 4 minus 2 is 2 to the 5th, is 32. So, a couple of those points you can't really graph because they're off the graph. But we've got 1, -1, 2, 0, and 3, 1. Looks like a straight line, but it's not because at 0 it's going to be way down here at -32 somewhere. Okay, so you can draw that graph through there. Looks an awful lot like x to the 3rd in this case. Something like that. Okay. Determine the largest open intervals for the domain for which this function is increasing or decreasing. Well, again, it's increasing the whole time. So you could say it's increasing from -infinity to +infinity. That will not happen every single graph, every single problem. But it does in this case. 1C looks significantly more complicated, okay? In essence, though, it has a x to the 4th And x to the fourth looks kind of like a parabola. It's not exactly a parabola, but it looks kind of like a parabola. But you notice this negative sign in the front, so that's going to flip it. A negative is a flip. And we know a 1/2 right here is a stretch. And we know this right here says left 3. And this right here says up 5. So we've got all kinds of things going on. We've got something that looks kind of like a parabola, only it's flipped and it's stretched and it's shifted left 3 and up 5. Think about your vertex formula. Okay, vertex formula, left 3 and up 5 means there's going to be a point right there. That's going to be the vertex of the thing that looks like a parabola. So we can make a table again. And you can choose any numbers you like, but since we're going left 3, it might make sense to put -3 in the middle of your table. Okay, you can choose any numbers you want, though, any numbers that are easy for you to work with. You know, maybe 0 is easy, maybe it's not easy, I don't know. So I'm going to do this one for you. I'm just going to, I've already done the numbers, so imagine me plugging the numbers in a calculator. If I plug in -1, I get -3. If I plug in -2, I get 4.5. -3 gives me 5. We already did that one. 4 gives me 4.5. And -5 gives me -3. We can do more numbers if we want to, but those are just the numbers that I chose. So -1, -3. -2, 4.5. -3, 5 already got. -4, 4.5. And -5, -3. So that kind of looks like a parabola, but it's not the same pattern. Remember, a parabola had a 1, 3, 5 pattern. That's definitely not a 1, 3, 5 pattern. So they asked that same question about intervals for which it's increasing and decreasing. So you can see this one's a little bit different. It's not increasing the whole time. It's not decreasing the whole time. It's increasing for a while, and then it's decreasing for a while. So if you notice, you know, it's increasing right here. This question is asking about the domain. So you would squash it onto the x. You would only talk about the x part. This thing is increasing. This thing is increasing from -infinity to whatever that x number is on that vertex, -3, bracket. And then you look at the other half of the graph. The other half of the graph is where this thing is decreasing. But when they talk about the interval, they want to know the domain. So you look at the x numbers for which that thing is decreasing. This thing is decreasing from -3 to +infinity.